So now we're going to look at inverse functions. And so this video is meant to be an introduction. And then the following videos which follow will go into some applications of inverse functions and how we use them and some examples. Okay, so the idea of an inverse function, and I apologize if there's some sound in the background. I'm having a lot of construction done this weekend. The idea of an inverse function is this. So remember when we talked about composition of functions? So when we compose two functions, we're looking at what happens to an input after it passes through. So let's look at, say, x here. X is our input. It passes through some function g, right? And the result, if you remember my washing machine dryer analogy, that would go through and you get your wet, clean clothes after passing your dirty clothes through it. And then we would plug this function into another function. And that, we'll just call it f. That's the name of our new function. And then, so we're plugging this. So remember, x is the input into g. And g of x is the input into f. So we're plugging g of x, the output from g, into f, and that gives us f of g of x. So that's not new information. That's what we talked about previously. So what is an inverse function? Well, intuitively, at least, an inverse function is a function that undoes what another function did to the input. So kind of a way to go backwards from what you started with. So if I start with an input x, right? So if I start with an input x, right, and then it goes into g, and it goes, well, the output of that, that's g of x, and if that goes into f, if the end result is x again, we call g is the technically left, well, would it be right? It would be the right inverse. G is the right inverse, meaning the right-hand side, because if you look at the composition up here, that's f of g. G is on the right. So g is the right inverse of f. And then if we compose them in the same way, so if I plug x into f first, and then I get f of x instead of g of x, like the previous part, and then I plug that into g, that will give me g of f of x. But is if, so up here, so this x here, that's f of g of x. That was our definition, the first one there, of a composition. But if we compose them in the opposite order, if this is also equal to x, we call this g of f of x. Then if I start with x, I put it through f, right? And then I take whatever comes out of f and I plug that into g, and I end up with what I started with, just like I did in the previous composition. We say f, or we can also just refer to g. G is also the left inverse. G is the left inverse of f. Now, if both of these hold, there are examples where some of them will hold if one of them holds. So we need both of these to hold. Excuse me. If both of them hold, we say f and g are inverses of each other, because if we pass an input through g and whatever comes out, we plug that into f, and I end up what I started with. And if I do it in the opposite order, plug it into f first, whatever comes out, plug it into g, and I end up with what I started with, we call them inverse functions. So if both 1 and 2 hold, meaning, looking here, if both 1 and 2 hold, meaning no matter what order we compose them in, we always end up with the original input, then we say f and g are inverse functions. Okay, so if, big if, both 1 and 2 hold. F and G are inverse functions. And that's really it. I mean, as far as a formal definition, just a little bit of intuition, that is the definition of inverse functions. And we're going to look at a couple examples in 1 second.